Hello, and welcome to Endgame. Thanks for joining us. Tonight's topic is exploring the future of energy storage with our guests, Psych and Atomic Carl returning.
Yay!
Enjoy the
Thanks,
show.
Volvo. Welcome, everyone. Thank you guys for coming. And Carl, thanks for coming on the show. We're really excited to talk about energy. And I guess before we get started, can you give us a little background about who you are and how you know so much about energy?
Well, I'm a software engineer. I work with Psych, but my history on energy and environment goes back to when I was in high school, and I learned all about acid rain and what our coal plants were doing to the environment. Since then, I've participated in many different environmental organizations, and recently I've become very enamored of nuclear energy. And so I've gotten to learn a great deal about nuclear and a great number of people in the nuclear and energy industry in general. Part of that is sort of researching alternatives and really testing out, well, why can't we do it all with renewable energy? And I started out a little negative, and I've come back a little bit. In fact, I've really tested my assumptions and come to the conclusion that a little bit of renewable is fine, and especially if we get better storage.
Awesome. And wait, when you said you work with Psych, do you mean like in psychology?
Oh, sorry. Poplapo is. Did I say Psych? Sorry, I meant I work with Poplapo in.
I was like, I don't think we work together, but I'm pretty sure I know. And then I was like, maybe you meant psychology, but awesome.
Yeah.
Yes. Cool. All right. So I'm your slide person. So yeah.
Great. So what you have here on the left is called the Baghdad battery. It was from Mesopotamia, and it is theorized to have been used for electroplating. The round dark thing in the middle is a copper cylinder, and the spike on the right is an iron spike, and the electric potential between the two is thought to have been used to electroplate a gold statue, and that would have happened conservatively around 200 AD, so very long time ago. And then on the right here, this is Volta's voltaic pile. So Alessandro Volta in the 1800s put together these stack of zinc, I think, plates and cloths soaked in seawater, and this created about 1 to 2 volts total. And I think it lasted for several hours, maybe up to 6 hours or longer. But you know, it's without reading an actual history, it's hard to get into that. So that's where we started, between 1800 and 220 years ago. So let's go to the next slide. And this is from the University of Oregon. It is called a Ragon chart of the energy potential of every modern battery technology. And you'll see lead acid on the bottom left. That's the technology that's been around for 50 to a couple hundred years and has been used in grid scale storage for many years. And then nickel cadmium, nickel metal hydride, alkaline, you are getting into very familiar consumer technologies. And then beyond that, there is the great...
I'm sorry to interrupt. If someone has joined late, they can't see the images. I think you need to turn off the slideshow and back it on again.
Okay.
Cool. And also feel free to get as close as you guys want if you can't read some of the stuff on the slides too. That's fine.
So there is the lithium ion and lithium polymer and lithium metal batteries. Those great, around the 250 watt hour per kilogram area. That's what your Tesla cars are filled with. Over a third or maybe half of the weight of those cars is battery. It makes them very ground heavy, but it's a terrific source of energy. It's very efficient. It's over 90% efficient in charge and discharge cycles. And you can see there's some arrows to the upper right for aluminum air, lithium air, and all sorts of very exciting future battery chemistries. And this is sort of the potential of where we think we can go. But unfortunately, go ahead and click to the next slide.
Oh, hold on, I lost the. Oh, here it is.
Well, my transparency didn't work. The left side's supposed to have a 1 megajoule, that's MJ, equals 278 watt hours. So if you remember, on the previous chart, that chart was all in watt hours, and this is all in megajoules. So that 250 to 300, where all of our exciting Tesla batteries was, that's the very bottom left of this chart. That's accurate. The lithium ion and the lead acid, those are accurate. Those are less than 1/20th of the energy of the worst coal source on the planet.
Wait, so what
Just
is
to
a watt?
clarify,
Oh yeah, go ahead.
I think I was going to ask you a question. Is a megajoule just a bigger measurement of energy compared to watt hours or megawatt hours?
Yeah. A watt hour is a watt expended over continuously over 1 hour. So if you say you have a 278 watt of power consumption for your computer, 278 watt hours will run that computer for 1 hour. So if you have 1 megajoule of energy stored, that will run your 278 watt computer for 1 hour. And so you'll see, you'll be able to get
That's not long
20
enough.
times to 50 times or more the amount of energy from a fossil fuel compared to a battery.
And what's
Now, of
also
course,
one other? What is a mega? What is sorry? What are the units? They're megajoules, and then what is L and the kg is weight?
Yeah, of course, kg is weight in kilograms, and megajoules per L is per liter. And so
So what
that's
does that
the
mean?
physical space, like the volume that battery will take up, and then the kilograms is the weight, is the heft of it.
So why and so are we typically evaluating batteries in terms of their? This seems like we're evaluating all of these technologies solely based on the weight or like the space that they take up. Is that a main method of evaluating these different technologies, or is it also kind of like the efficiency of them, or does this display the efficiency as well, the relationship between the weight and the megajoules?
Right. Well, of course, we would have a 5-dimensional graph and have a very hard time visualizing that. Of course, we are in VRChat, so maybe we'll make a world someday
Next time.
Work on
to
that.
visualize all battery technologies. But in 2 dimensions, in 2 dimensions here, it's called the Ragone chart or the Ragone plot, I think. And so it focuses on the physical space. That's the volumetric density and the physical weight or the gravimetric density. And so when you talk about the amount of energy you need to store for 10 hours or 100 hours or 30 days of energy storage, well, that's expressible in liters and kilograms. And of course, kilograms of mass is roughly linear, corresponding to the amount of materials we need to take out of the earth. It's every kilogram of material we take out of the earth is corresponding to between, let's say, 10 and 1,000 kilograms of mined material. So vanadium or something might mean 1,000 kilograms of mined earth per kilogram of vanadium, and something like coal would be closer to 2 or 3 kilograms of earth per kilogram of coal.
Okay.
But it's roughly the same scale. So think about that in terms of the amount of mining, the amount of resource extraction. It's all relatively similar. And so the density of these storage mediums, or these fuels, if you will, is very important. And again, batteries are very efficient. They're over 90% efficient in charging, or lithium batteries are. But how efficient is coal to charge? It takes thousands to millions of years, of course.
Yeah.
And
Yeah.
Regents, did you have here, come to the
Oh yeah. So,
Yeah.
so
we
this,
enable the images. Good
Oh
news,
yeah.
guys.
Thank
so
you.
this chart would be useful when you're talking about vehicles or like a portable storage solution where weight is a key factor. But in a grid, like batteries are not a power source. Batteries are a power storage where crude
Right.
oil and such, you're burning it once. So they're
Right.
not even equivalent, correct?
Well,
Because you're not
I'm
using
sorry to
lithium
put
as a
some
power
hard
source.
realities. Yeah, I'm sorry to put some hard realities on this, but when you're talking about 100 hours of storage for a 3-day or 4-day period when the sun when we're overcast or when there's a lull in the winds, or even worse, 30 days to 90 days of storage when we're in the middle of a typhoon in Tokyo, the volume and the weight for storing that much energy is enormous. We have a substation here not far from where I live, and it would be over 600 meters tall if we were
But
going to
you
try to
wouldn't
put
use You wouldn't use a battery for that. The battery's there to stop your peaks and valleys over a normal day. You wouldn't use lithium. Isn't being used for long-term storage anywhere on Earth.
And you are right, but not everyone would agree with you. Some people would say, well, we can use all the wind and solar energy that we can get. We just need a little bit of batteries. But little bit is not quite accurate. As you're right, Rejinx, we need a huge amount of grid scale storage in order to satisfy a 100% renewable energy target.
Let me
people don't
just say
realize
this
that.
as well. Isn't it basically? Isn't like basically all our energy that we use? It's on demand, and that is the huge problem because, like, obviously,
That is it.
It's so hard to store energy. It's so hard to store electricity. That's the whole
Right,
challenge,
and
isn't
that's the entire point of this chart. But this is as dark as it gets, and I want to bring us back to a little bit of hopefulness, because maybe there's a chance that we can get to 5 or 10 megajoules per kilogram someday with some kind of storage technology. That would certainly be fantastic. But that's the kind of opportunity that we need to approach if we're going to get any kind of grid scale storage with a chemical battery. And when we get to the end of the talk, I'll go into all sorts of different kinds of more dense utility scale options that we have. So let's go to the next slide.
All right. I'm just gonna toggle that so people can.
So there's this wonderful YouTube channel called Cortex, Coreteks, and in one of his videos about the next PlayStation, he talks about technology disruptions and how a new process technology traditionally takes a while to spin up, and then it accelerates, and then it plateaus. So, for example, disk drives were superseded by smaller disk drives, 3.5-inch drives, followed by solid state drives. And you see that solid state drives 15 years ago were terrible. But as recently as 5 years ago, they started getting really good. And now they're the best storage option for your desktop computer.
It seems like
And
Moore's.
so
Is this
what-
related or based on Moore's law of like doubling everything,
This
doubling
is-
in efficiency?
Well, this is exactly how Moore's law operates. Intel, when they create a new process, a new die shrink, they are following
Die
this
shrink?
S-curve. Well, it is the number of nanometers between transistors on your CPU is what I mean by die shrink. And the number of, the space between transistors relates twofold. both to how many transistors you can have on a physical piece of silicon and how energy efficient that is. So Moore's law, it gets a double bang for the buck. It gets both materials efficiency and it gets energy efficiency every time that gets more that is improved, and there's almost no lower limit. There's a very, very infinitesimal lower limit to how small we can get between two transistors with, you know, some theoretical future technologies. I'm stumbling over it. It's much smaller than we have today, and we keep pushing that boundary, even though it's a little more asymptotic. And people talk about the end of Moore's law. We have gone a tenfold improvement since we initially thought we were fighting the end of Moore's law. So there's always a little bit more that people seem to find, and it's fantastic. Even if we're not doubling every 18 months, we're still making pretty decent improvements. So I would say for CPUs, we are, for any CPU process, we're starting to plateau. And in software and in GPU architecture, we're finding a new disruptive curve where we have better multi-core processing, making a new curve of disruption.
Interesting.
So
Okay, so
let's talk about that scale problem, and let's go to the next slide. So suppose that we had as much battery as we possibly could get. Could we really subsist on 100% solar or 100% wind? This is from a paper from Ken Caldeira. It's something called like the geopolitical constraints of storage. And what it's showing is the overbuild. And on the left, that's a linear scale. And on the right, that's a logarithmic scale. So this is these numbers, 1 through 4 on the left and 0 through 10 on the right, is how many multiples of the capacity of each renewable energy source we would need to satisfy 100%, or sorry, at the bottom it shows you the percentages. So 20, 40, 60, up to 100% of our energy needs using renewables.
What do you mean multiples?
And in the bottom left chart,
multiples of
what was that?
When you say multiples, like multiples of what?
So if you consider the peak output of a wind turbine or a solar cell, that multiples is what we're talking about. So if you need 100 watts to run your life, you have a 100 watt solar panel, that's great. But in order to have 100% availability, if you have 32 days of storage, you need about 1.5. Solar isn't on here. So say a 100 watt wind turbine, you would need 1.5 times 100 watts, so 150 watts of wind with 32 days of storage. And remember, 4 days of storage for Seattle is enormous. It's over 600 meters tall.
Oh, so so if I understand it correctly, then basically different lines represent different time frames, and so the idea is that if we're not able to store anything, and this kind of comes back to what was being talked about before, but like if we're not able to store anything, the curve increases very quickly and it basically is impossible. But even with 1 month of storage capacity, which seems like it would require a huge amount of batteries like you were just talking about, you're still seeing that increase. Is that the kind of idea? Is that like the point of this chart?
Exactly. It is that it does take quite a bit of capacity to store, to generate extra energy for storage and to fill in the gaps.
So what's the column on the right then? Because on the right it looks like that turns around.
Well, on the right is exponential. So that first tick on the right chart is 90%, and that is between the last and the axis. Yeah.
Okay, I didn't notice that. This is like in math in like 8th grade when they switch the labels on the graphs and you're like, oh, look what changes. Well, okay, so this is just for people who might not know my like 1 times table. Yeah. This is just for so on the left. So on the left we have 0 to 100%, and then on the right we have 0 to this is increments of 20, and it's really there's a big gap, and then it goes from 90 to 99%. So it's showing that to get that, it's kind of like, is that kind of like the last mile, so to speak, of fulfilling energy? Is basically gets almost impossible to do. Becomes impossible.
Yeah, and that's why the most honest deep decarbonization plans don't completely eliminate fossil fuels, don't completely eliminate baseload. Even with nuclear, there's a few places where we just need that extra on-demand energy spikes for uneven demands or for outages and for other reliability concerns.
Or just coronavirus. I mean, if you think about it, it's kind of interesting thinking about all the internet outages and things. And I know we're not gonna. Coronavirus is going to be a talk next week or the week after. So we're going to come back to that. But I know we're going to do another one.
It's changed a little.
But yeah, just to stay like on topic, but one thing to mention is that here's an example where, let's say we had all the batteries in the energy storage. It seems like all of a sudden people who might be, especially service workers or people who might be working out and not using as much energy because they're all in a restaurant, or they might be outside working outside, all of a sudden those people are all home using their computers and using the internet. And so what would happen if we were on 90% renewables? We'd probably be, I guess, we'd be in that area basically unable to meet the demand. And
it really depends. Yeah.
Interesting.
So let's go to the next slide.
Oh, do we have a question? Or
go ahead.
I think
Dragon.
This virus is going to expose how, I think in the end we're just going to have to change our lifestyles at some point, I think, to get to a good solution. But that's conjecture. Go ahead.
Yeah.
Well, a lot of people think we have to change our lifestyle to meet the challenge of climate change, that we need to reduce our energy consumption. And this is the reality of our energy sources. Oil, natural gas are both collectively over half of our energy demand. Now, in 2020, that's going to take a little slip down because we're not driving as much, being in self-quarantine. There we've got a little small missing.
Like, what's it? This water's
the water
for the first time in like 200 years or something.
And China has a lot less smog. Although I mean, and also, but that's also interesting because the pollution is also helping to keep the Earth cool potentially, which is kind of a whole other topic. But
right, from the atmospheric, the shading, so that's a really quick piece of reality. Let's go to the next one quickly before I get really depressed. So when I talk about how massive chemical batteries need to be, we have so many other options. We have different kinds of energy storage that satisfy different needs. They have massively different densities. Like pumping water is quite a bit more dense and more affordable than simply building batteries, but it doesn't react as quickly. And so we want something like lithium-ion batteries for charging and discharging quickly. We want perhaps even some supercapacitors to maintain supercapacitors at the bottom to maintain the life of our batteries.
That's what I was gonna ask.
So if you could just point to what he's talking about.
I'll point. So first, can we just understand? So the two axes here, the x-axis down here is system power ratings, and then this is discharge time. So what is a system power rating? How much power it can create and how long it takes to discharge? Is that the idea?
That's the instantaneous power dispersal. So a supercapacitor or a superconducting energy magnetic material peaks out at around 10 megawatts, but hydropower and compressed air, they can start to output gigawatts of energy. And so, and in fact, lithium and lead acid batteries are similar. So a lithium battery might be able to hold a longer charge, but it can't produce the raw energy output that a lead acid battery could.
Just so you know, you have to write really slow because of the IK
Yeah.
issues that
Oh.
are still an issue.
It looks like
Yeah,
Gemini.
You're writing in another language site.
Oh my god, that's what happened last time. Someone wrote an equation and I was like,
Yeah.
wow, I didn't realize, I just thought their handwriting was really bad.
Yeah, that's
Wow.
It's okay. It's okay. You can still like
All right.
circle things kind of and put dots up there and stuff. So
Yeah,
Well,
circles and
all right.
lines do a little better.
Okay, so high energy supercapacitors are here. And then what's this stuff? Like what's the trend? So I see like lithium ion batteries, we see like hydrogen fuel cells are up here in the green. So
Mhm.
what's going on as we get further up to the right in this graph?
As we get further to the right, we reduce the round trip efficiency of our charge-discharge cycle. But we're working with physical properties that produce so much more raw power. A generator from a hydroelectric dam or a pumped hydro system just produces a terrific amount of power over a long period of time. But it doesn't react nearly as quickly, and it's not nearly as efficient as a battery, a chemical battery, or a capacitor.
But again, that is coming back to the point that I think Rejinx made. This is confusing to me because we are talking about, aren't we talking about energy generation versus energy storage? So
Right. Well, we've covered energy generation. You know, we can get say 60 to 80% of it with solar and wind, and we only need a place to store it. And the better that storage efficiency, so the further left you go, the more efficient your storage is going to be.
That's what it's all about, isn't it? I mean, especially now, like everyone's going towards EV vehicles,
Right.
electricity. You know, it's all about storing energy. I mean, that is literally, if someone can invent something, I think that's the new paradigm shift in terms of technology. You know,
Yeah.
it's got to be
You
light,
can't count on
efficient.
that though. Like,
yeah,
it
of
would be
course you
nice
can.
if someone
I mean, that's it.
invented something cool, but like if
Yeah,
that
but
doesn't happen, then we gotta.
Yeah.
That's the thing,
And-
though.
and
because
remember, we-
you know,
we
Isn't
were
charge
sitting-
times between electric versus gasoline so insignificant still? Like it's so far apart in terms of
30
taking
minutes
time to
for
fuel. Yeah, it's
Well, all I know is
a
like,
couple hours
I
depending
want
on
to
the
buy
car
an
and
EV
the
vehicle,
quality of the
but
battery
it's so
too.
expensive.
Hold on, you
You
guys
know,
are
it's
both
just-
talking at the same time.
Sorry.
yeah, no, but this is true.
Yeah.
Batteries, electric batteries, but the storage and capacity and what is the future? We'll get to that in a second. And Rejinx, I also saw you had a question or point.
Oh yeah, so I wanted to ask actually about. So I've heard about the water storage, which is basically like using a hydro dam, except when you have excess energy, you just pump the water up, and then you just run it
Right.
back down. But how does the compressed air one actually sounds pretty interesting? Do they create just really large containers to compress air, or do they create many small containers? Is it at really
No,
high
they will-
pressures?
We will actually, we would use underground caverns, things like a salt cavern formation that's surrounded by pockets of water. And so we're using enormous amounts of air and producing moderate changes in pressure, enough change in pressure in order to drive an energy system, a pneumatic system that drives a generator, but it's again, it's a slightly less efficient than pumped hydro, and it really depends on the specific implementation. But yeah, when you want to
And that
think
sounds
of,
like it could be dangerous if it would reach the water table and just cause geysers everywhere.
well, this would be kilometers underneath the earth where there's already tremendous pressure and you know many kilometers of rock and water to go through.
Wait, this is
Sounds
natural. This isn't
unreliable.
contained.
Right.
Hold some is
Well,
interesting. And
salt
what was
mines
your-
don't go kilometers deep though. They go maybe 1 kilometer would be like the maximum a salt mine could be.
Yeah.
But
Was there-
Yeah,
was there
for a
fighting-
practical.
I was trying to ask is this a contained unit or is this actually in a natural environment that you're just having to make this artificial wind turbine system in it? because any kind of small fracture or imperfection in the formation could really reduce the efficiency of this generation system of wind for pneumatic energy like that.
Yeah, that's the idea, and so it is one of those up and coming systems. But we do have natural formations like the salts under New Mexico, where we like to store nuclear waste, that are self-sealing, that they are these salt formations that don't permeate water, and they're very solid and very deep. And so there are a few. I know that we tend to use more liquid containment, but it is for a very, very large storage. It is possible. And you're right, it could leak, but again, it's only a little bit of air, and so we're talking about a matter of hours in terms of storage.
More than the actual escape of the air.
And
that's without like any kind of side pressure that's going to cause it to disrupt any kind of smoothness of the actual equipment. I don't know how you're going to make this efficient with just natural formations.
I'm not perfectly versed in the implementation details, but I do see that it is below pumped hydro storage, and whereas pumped hydro storage even has evaporation to contend with, and so it's not perfect either, but it is better than compressed air storage.
Okay, interesting.
So when we get to the bottom of this chart, we talk about supercapacitors, and that's for a very special kind of storage that we call a frequency control. And in America, because we have a lot of coal, we have one of the most efficient forms of frequency control there is. So if you'll go to the next slide, it is these enormous steam turbines from the coal plant that are spinning at a constant rate, and the inertia of this enormous turbine is what is called a spinning reserve. And so small fluctuations in the energy output by the thermal plant, by the hydro plant, cause very minor perturbations in the spinning reserve. And that's part of the engineering of these enormous systems, is to keep all of these generators synchronized across the three major grids in the US. So everything in and around Texas is one, everything west or approximately west of the Mississippi, and everything east or approximately east of the Mississippi is, in general, those are the three systems. And so that frequency, that 60 cycles a second, represents hundreds to thousands of these turbines spinning around and around in lockstep.
And they're
That's so
powered
bizarre
by...
sounding.
It's mind blowing how that is
Yeah.
achieved. To be honest,
Yeah,
because,
it's crazy that... Yeah.
I mean, the thing is,
Go ahead.
yeah, exactly. I mean, the fact that you plug your little hairdryer in, but like it all runs on 120 in the US, and everything has to be synchronized through the whole grid.
Yep.
Oh.
And if one thing's out of step, well,
I'm sure there's transformers in place for that.
Its
I'm sure.
neighbors pull it along. Its neighbors pull it back up, or everyone's lights start to change color, or they start to dim. It's called a brownout. We used to have those in California back in the Enron days, and
Some people
in
used to have them in college.
Australia. Wow. And in Australia, in fact, recently, in the last 2 or 3 years, they have had frequency control problems. That's what the big Tesla battery exists to serve. It has not actually eliminated any fossil fuel storage. It has not provided a significant amount of grid backup, but it has made a lot of money by keeping that frequency stable. And without coal power in South Australia, it's exactly that. It's a buffer. So let's go to the next slide and talk about a little more long-lived. So longer lived than chemical battery or a lithium ion battery or a lead acid battery is this thing called a vanadium flow battery. And that's where we have, instead of everything layered together like the voltaic pile, you remember that? All of the anode and cathodes are in their own separated soups. And we literally have to apply more energy to extract the energy from these flow batteries. These are more things that we put in big caverns underground. We might, find two isolated cavern systems and put vanadium in one and another, the anode in the other. I forget what chemical that is, but this is another massive energy storage system where we need a lot of physical space.
I don't really understand what these things are. Like what?
Well, these are tanks of chemicals, and they have different electric potentials, and when they meet in the middle, they discharge
and generate electricity.
Yeah, that's exactly how it works. I mean, that's very simplified, but this is an overview, and I'm not a chemist.
That's fine. I'm just trying to understand the interest. But you're saying it takes more energy to generate the energy. Then it's a net negative.
Well, it's not negative. It is positive. Otherwise, we would never build them.
Yeah.
It takes a minor amount of power to move the chemicals into the membrane.
Alboy, did you have a thought?
Yeah. You said vanadium?
Vanadium, yes. It's a chemical that comes up with steel commonly.
Okay. Is it common? Is it rare?
It is fairly plentiful because we produce so much steel. I haven't looked
so it's
on...
a byproduct.
Yeah, it is essentially a byproduct. It's used for various electronics, I think, and it is a potential for a battery technology because there is simply so much of it around relative to its demand.
Yeah.
The governor of Washington loves to talk about it because we produce some vanadium cells in the state.
Oh, okay.
Is this used in any major place? Is this used?
There are a few minor places, I believe. I would have to double check. I know that it might be one of the candidate technologies for our ferry system.
Oh, cool.
Interesting. Huh.
So let's go to the next one. This is where we get to the exciting. This is Australia's Snowy 2.0. And I have some notes on my Trello board. Oh, where'd it go? There we go. So that Snowy 2.0 has a maximum capacity of 230 gigawatt hours. And this costs...
Let's just also, because I don't think people can read what this is. So there's a reservoir here, and there's a tunnel coming to a power station. And so it says pumping this way, generating is this way. And then they have this, an intake here, a reservoir. So what is that? What's going on exactly?
So when we need to charge the system, water flows from left to right. And when we discharge, we flow from right to left. It's that simple. Yeah, this is pumping water, physically pumping water from one lower reservoir to an upper reservoir and back.
And how does that generate a net positive electricity?
Well, it's over time, and remember, this is storage, not generation. So we're about 60 to 80% efficient in pumped storage, in pumped hydro storage. And so when energy is plentiful, we add it to the system. And when we have the demand, we remove it from the system.
So this is not generation. Okay, so this is just storage, and it's a way to kind of keep extra capacity and energy that you can take out of the system and put back in. Okay, like the Tesla battery, but maybe the better
Yep.
system kind of thing. Okay.
And remember, this has a much higher net power output than batteries. If you remember our earlier slides, we're approaching gigawatts of raw output, and we also get the side benefit of that spinning reserve. So pumped hydro is very exciting, and I think it is essential for all large-scale electricity storage.
What about weather?
And-
Does that affect it? You know, like adverse weather events affecting the water?
Well, of course. Yeah, well, rain will benefit because you can typically drain from your lower reservoir for free, and any rain that goes into your upper reservoir
is
a net benefit, a net generation of energy.
Interesting. Regents, did you have a?
So is there a plan? Because it seems like you'd be able to retrofit current hydro systems that normally use mountain flow from snow melt and stuff like that. Is that like, can you retrofit an already existing dam, like, I don't know, the Hoover Dam or whatever, to add this? So, because basically that's all we're doing is the same as this. We're just letting Mother Nature fill the top basin instead of the bottom basin.
That's absolutely right, and there are plans for. I think there is one right now in Nevada for the Hoover Dam to be used as pumped storage in addition to it's very exciting. So the economics of this project itself, this is about $5 billion for Snowy 2.0, and so that is about 46 watt hours per dollar. And if we go to the next slide, I have a little bit better news. This is the Gordon Butte Pumped Hydro Project in Montana. It's very similar to the one you just saw, except the upper reservoir is, of course, on the left. And so there's a place in Montana called Gordon Butte, and there is a project that is, they say, shovel ready, that will let the city of Seattle and all the neighboring municipalities benefit from a great deal of energy storage. The scale of this is enormous, and in fact, because of the favorable terrain, it's supposed to cost only $1 billion, and is supposed to provide 1,300 gigawatt hours. That's 1.3 terawatt hours.
$1 billion is pretty cheap for any sort of damage project.
True.
Yeah. And so this, they're saying, is supposed to come in at over 1,300 watt hours per dollar. And so we've gone over 2 orders of magnitude up between Snowy 2.0 and Gordon Butte. So this is pretty exciting, and I really wish that we would get some funding applied to this, because I'm tired of seeing more natural gas development in my state.
Yeah.
That cost is including transmission from Montana all the way to Seattle, where you could a Seattle worth of energy all at once from Montana.
Well, right now we send coal. We send a couple gigawatts of coal from Montana to Seattle. So the transmission infrastructure already exists.
Okay, cool.
I mean, the thing is, these are state problems, and the thing is, you should really, petition to your governors, however the process works in the US, because federal wise, they don't care. It's your state,
Yeah,
one
sorry,
of the things... Atomic, and then...
the right people.
Yeah, hold on. Atomic, do you want to respond, and then Ghoster?
Oh, I would say that, and that's part of the work that I do with environmental organizations, is I advocate for these kind of things, and I try to get, like, my local 350 and Extinction Rebellion to advocate for projects like the Gordon Butte Pumped Hydro.
Extinction Rebellion! Yes. Ghoster.
Oh no! One of the things about pumped storage that might have been mentioned is that terrain is generally not favorable for pumped storage. You can only put it in certain places. Yeah. So I guess this is one of the better ones. Probably what? Maybe a 500-foot terrain difference from the lower reservoir to the upper?
It might be something like that. I'd have to go back and look, but it is very, very favorable.
But basically, you need someplace high that you can put a reservoir, and then have someplace low that you can let the water drain down into within close proximity of each other. And that's like one of the worst things to have.
Yeah, and Switzerland, I think, is another example of where they have a huge amount of pump storage. They're probably maxed out in terms of what they can build, and it doesn't scratch a dent in the total demand of Europe. So we could say we could improve the pump storage by a factor of 50. That could be the world's limit. And in a country like Switzerland, it might be 2 times what they have, and that would be an enormous undertaking.
Wow.
I mean, there seems obviously there's risk factors involved. Obviously, you're building, you're damming up water. That's always going to be a risk to people downstream.
Right.
Devastating dam collapses. That could kill thousands.
Yeah, and that's why they have these safety features. Like if you'll notice, the inlet to the reservoir is deep underground. And so the worst thing that could happen here is if that upper reservoir collapsed and flooded the entire mountain area and caused a landslide, or maybe the lower reservoir collapsed and wiped out a section of the highway. But you're right, hydroelectricity is not perfectly safe.
But it seems like a potential, future area. Yeah. So as we head towards the end of the show, is this what do you see as the future of energy storage? I mean, if you had to kind of predict the next, 50 to 100 years, where do you see us going? And what do you think the future?
I think you're being a bit too ambitious there.
Well, if we survive, it will be because of the technologies we see today. It will be the combination of chemical batteries that are between 1 and 5 megajoules per kilogram. It will be pumped storage. It will be vanadium batteries. And unfortunately, it will include fossil fuels. But if my name gives it away, I have another option. It is an energy source. Yeah, that is 1,000,000 times more gravimetrically dense than fossil fuels. It's nuclear energy. The only problem, of course, is that you can't recharge it. Yeah, you can't recharge it without a supernova. So let's take everything we can to make some safe nuclear, because that's sort of the missing gap. And if we survive 50 to 100 years, it will be the combination of fantastic storage solutions, nuclear energy, and zero carbon generation like hydro, wind, and solar.
Awesome. Cool. Well, we'll have to see.
I think Rejinx has a comment.
Yeah. No, I thought we were done. So I was just gonna ask questions to fill up time.
Sure. We have
we look into the economic side of it. So right now, I know that this epidemic isn't helping, but oil prices over the last 5 or 6 years have been annoyingly cheap. And do you see the economic side of how do we value fossil fuels appropriately to make these kind of projects more economically reasonable? Basically oil should cost, because it's a non-renewable, much higher, but because we've learned so many ways to quickly pull it out of the earth and we don't have storage for it, prices have plummeted. Or do you work, or do you look into that kind of stuff, and any ideas on that kind of stuff, the economics
Absolutely.
of it?
I spent over 100 hours volunteering for Washington's initiative 1631. That would have been a carbon tax in the state of Washington, and that carbon tax would have been at $25 per ton of CO2, or about I think it was either 7 or 15 cents per gallon of gasoline. Unfortunately, that was defeated, but I definitely will promote Carbon Washington, which is my local organization for promoting carbon pollution pricing. I'll promote, let's see, the Energy Innovation Act in the United States is a federal carbon tax proposal. That's called a tax and dividend, where it will cost you if you burn fossil fuels, but if you don't, you will reap a dividend back from the government, back from the people who are spending that carbon pollution. Overall, a carbon price of between $10 and $15 will make all nuclear plants in America economical. It would make projects like the Gordon Butte Pumped Hydro Station especially economical, and something like $20 to $50 a ton of CO2 would make Snowy 2.0 and make multiple Snowy 2.0 projects in Australia economical.
Thank you.
Yeah. Interesting. Cool. Well, does anyone have any last questions before we wrap up or anything?
Do you think we're gonna
Burning
make
desires
it to 2050?
Right.
I don't mean, I don't mean,
We will.
joke. I mean, what can we do?
Well, I definitely think we need national priorities to decarbonize all sectors of energy production. We need to switch our personal transport options to things like mass transit, electric bikes if it's possible for you, electric cars if neither of those are possible. But I'm a city-dwelling futurist, so I tend to think that cars are something of the past. If the lack of pollution from the coronavirus self-quarantining is any indication, doing more VRChat, doing more online virtual socialization, you're doing a great job.
Awesome. Yes. We are helping the planet, so
there you go.
Awesome. Well, thank you. Well, thank you for this interesting, I don't know much about renewable energies. I mean, I'm for them, but it's interesting that, just like any problem, there's complexities, there's pros and cons, and, there's things that sound good, like eliminating straws, but then there's solutions that actually have a huge impact. And, it's like, how do we actually make a big impact, and what are the buzzwords and kind of things like I hear people talk about nuclear and these other kinds of power sources, but really understanding the cost benefit analysis, I think, and the trade-off it's been very interesting to learn more about with these charts. So thank you.
Energy storage.
Cool.
We need
Yes, well,
Thanks everyone.
Thanks guys. Hold on, let me play the outro music and we can go ahead and come up on stage and take a picture. Group picture after I turn off security. Okay, security's off right now.
No
Yay.
bouncers.
Alright, where's my
Yay.
battery avatar?
Atomic, you can come up to the middle
You are
here.
Yeah, you gotta get in the photo.
In the middle. Nice. And what do you want us to say on pre Atomic? Any kind of praise for energy? Atomic energy?
I'd say, the best storage is the power of stars.
Okay, the best storage is the power of stars. That's the power of stars.
Star power.
Power of stars. Power of stars on 3. Power of stars on 3. Oh god.
Okay.
Combination of stars and power.
Power of
The power of stars.
Yay! Yay! We're officially over. Thank you guys.
Awesome.
Oh, also next week or the week after, I have to figure out when we're having the next Endgame. We are going to talk about the psychological impacts with the coronavirus. So stay tuned. Join our Endgame, endgamevr.com to join our Discord.
Endgame's back, yay!
Yeah.
Not like you have anything better to do.
Yeah,
Right, I'm
Exactly.
on
Might
time.
as well come to Endgame.
Oh yeah, you can't be traipsing all over the country.
Yeah, exactly.
Oh,
That's exactly.
Hey,
it all makes sense now.
Not
Traipsing, I like that. Yeah. Like shame.
No, you're.
Yeah.
You're busy.
The thing is, like, I mean, it
Sorry.
affects so many
That's all right.
businesses. I mean,
Yeah.
it's just gonna have to go into the top because.
No,
like,
but
Yeah,
yeah,
but actually,
maximize that. Do another one next
our
time.
business is doing great though because of, I mean,